In this lecture, we're going to describe how we quantify transcript levels. And you're going to see that we're going to use many of the statistical concepts that we described before. We're going to use modeling. We're going to use the Poisson approximation. We're also going to use linear models. And we're going to use a maximum likelihood estimate. So just as a reminder, a gene can have several transcripts. Here's an example of such a gene that has 13 different possible transcripts. So now, to illustrate how the data is generated, we are going to start with a cartoon like this. So in this cartoon, we represented transcripts with color. So we have the green transcript, the orange transcript, the blue transcript, and the purple transcript. Now for each one, we have several copies because there's different levels of transcript expression. Over here on the right, we're showing some notation that we're going to be using later. It gives us the length and the number of copies. Now the reason the length is important is because once this turns into reads, as shown here, we have more reads of the first one than the second one, even though the second one has more expression. Why? Because this first one is longer. Therefore, there's more pieces. So 3,000 times 4, for example, is bigger than 1,000 times 7. So this is what we're going to get in terms of read. We're going to have all these little pieces. And we have to figure out, just from these pieces, what these numbers are, 4, 7, 1, and 3. So let's continue. So we're going to use statistical modeling to decipher what the transcript levels are. And to do that, we're going to use a statistical model, and I'm going to introduce some notation that it uses. So P of f is the proportion of the total amount of sequence that comes from transcript f. And that is equal to theta f, that's a new term I'm introducing, times its length. So theta is the transcript expression. This is going to be the parameter of interest, but it's relative to the total expression. That is what we're going to work with. That is what we're going to try to estimate. And that's the quantity that biologists care about. If in a particular experiment you just happen to get more reads than in the other, you shouldn't report more expression. You should just report, or at least that's what we're doing these days, where we're reporting the transcript expression relative to the total. So using the previous notation, this is kf, the total number of copies of fragment f, divided by the total amount of sequence. So in this slide, I'm introducing a new term, yf. Yf is the number of reads coming from transcript f. This is going to follow a Poisson distribution. That's the model we're going to use, with rate theta f, the expression of fragment f relative to the total, times its length. Why do we multiply by length? Because the longer the transcript, the more reads there are to pick from. And why is it Poisson? Well, you can think of it this way. Yf is basically a sum of zeros and ones. Each read either is or is not from transcript f. So we're taking a sum of binary data where the total number of things we're adding, n, is very large. That's the number of reads. And the proportion that are from this fragment is very small. So this is similar to the lottery example we gave in a previous model. And here the law of small numbers tells us that a sum of binary outcomes with a large n and a small p can be modeled with a Poisson. These are two examples of papers where the Poisson model is described for RNA-seq data. In the next module, we're going to show how using this model, we estimate, using maximum likelihood estimate, the transcript levels for each transcript within a gene.